A small creek once stopped a transcontinental railroad in its tracks. Not the creek itself, but the gorge it had carved over thousands of years, 150 feet deep, 650 feet across, and the Union Pacific had 85 days to bridge it. The structure they built, a pine timber trestle spanning that gorge in southeastern Wyoming, was completed in April 1868 and was ready, according to one contemporary account, for the heaviest trains. It had no steel, no concrete, only timber, hand tools, and a workforce under extraordinary pressure. This is how wooden trestle bridges made the American railroad possible. In 1862, Congress passed the Pacific Railway Act, which designated a transcontinental route and provided government bonds to fund the project, along with large grants of land for rights of way. The incentive was direct. The more track a company laid, the more land and money it received. The Act provided loan bonds for each mile of track laid, $16,000 per mile on level ground, with the figure rising considerably in mountain terrain. Speed was not merely desirable. It was the financial model. That pressure shaped every engineering decision along the route. When construction crews encountered rivers, canyons, and dry gullies that filled with snowmelt each spring, they needed a solution that could be built fast, from materials already available. In the United States and Canada, cheap lumber was widespread and readily available in nearby forests. And unlike stone or iron, it required no foundry, no quarry, and no lengthy procurement chain. But what made timber the right choice was not only availability. It was a structural logic that engineers were only beginning to fully understand. Construction crews built trestle structures as they worked ahead of the track layers, crossing rivers, canyons, through mountains, and over dry gullies. These were not specialist craftsmen working at a deliberate pace. They were large, mixed crews. The Union Pacific employed more than 8,000 Irish, German, and Italian immigrants, while the Central Pacific's workforce included over 10,000 Chinese laborers. Many had no prior construction experience. What they brought was physical endurance and the willingness to work at height, in weather, with hand tools, on structures that were being designed and assembled almost simultaneously. The cross-country railroad was built almost exclusively with manual labor and hand tools. The knowledge of how to build a trestle was passed through the repetition of each bent, each cap, each stringer, hundreds of times across thousands of miles. The basic unit of a wooden trestle is the bent. A pile trestle, the most common form, consisted of bents spaced 12 to 16 feet apart, each bent made of 3 to 5 round timber poles, pounded straight into the ground by a pile driver. The outer posts were angled slightly outward for lateral stability. For deeper crossings, a different approach was used. Frame bents used square-cut timber rather than round poles, with subsills or mudsills acting as the foundation of the structure. These frame bents were built in sections, typically 10 to 15 feet high, assembled flat on the ground, then raised into position. The timber itself rarely came from the immediate site. The timber for the Dale Creek trestle came from the forests of the upper Midwest. It was pre-cut, transported by rail, and assembled on location, a logistical chain that itself depended on the very railroad being built. Once the bents were set, a horizontal cap was placed across their tops. The top of the uneven posts were cut to the proper level for a cap, which in turn supported the stringers and planks that held the rail. Each element transferred load downward, rail to stringer, stringer to cap, cap to bent, bent to ground. For the tallest structures, individual sections of the bent were built flat on the ground as a single or double story, then lifted on a high line where they were lowered and fitted onto the rising structure. The process was then repeated for the next level. If alignment between sections was imprecise, the load path through the structure would shift. Over time, under the repeated weight of loaded locomotives, a misaligned bent would fail before an aligned one. There was no margin for error and no way to inspect what you could not see. The Dale Creek structure in Wyoming made this logic visible at its most extreme. The original wooden trestle measured approximately 650 to 720 feet in length and rose to approximately 150 feet above the narrow gorge below. Its piers were built from native Wyoming stone without mortar. With stone foundations and wooden supports, the structure raised the track 120 feet over the bottom of the ravine, and required guy ropes to hold it steady in the wind. When the first locomotive crossed, the engineer on site, Samuel Reed, watched the bridge move. Reed ordered that ropes be tied to the bridge and anchored to the gorge walls. Those ropes were replaced with cables as soon as they could arrive. Some locomotive engineers refused to stay in the cab during the crossing. The bridge held. The line moved west. The railroad companies first built temporary wooden trestles and bridges that they later replaced with more durable and permanent iron structures. Wood, though prone to decay and fire, was cheaper and more obtainable. This was always the plan. Wooden trestles were not intended to be permanent. They were instruments of speed, built to generate the revenue that would eventually pay for something better. Untreated lumber only lasted about 20 years, and locomotives could easily cause the wood to catch fire. The question was never whether these bridges would last. The question was whether they would last long enough. The wooden trestle at Dale Creek was replaced by an iron viaduct in 1876, retaining the original granite piers. The iron bridge was itself eventually made obsolete when the Union Pacific rerouted the line entirely. An 1,800-foot tunnel combined with a 900-foot dirt fill over Dale Creek eliminated the crossing altogether, reducing the line's elevation by 250 feet. The wooden trestle had served its purpose. It opened the route, generated revenue, and bought the time needed to build something permanent. Timber and iron trestles were extensively used in the 19th century, the former making up from 1 to 3% of the total length of the average railroad. That figure understates their significance. The trestles were disproportionately located at the most difficult crossings, the places where, without them, the line could not have continued at all. Long before standardized steel sections and engineered concrete, the expansion of the American railroad depended on a simpler calculation. What material was available, what could be shaped by hand, and what could be assembled fast enough to keep pace with a government deadline. Timber answered all three questions. Not because it was ideal, it decayed, it burned, it moved in wind, but because it was there, and because the men who built with it understood its limits precisely enough to work within them. In the 21st century, steel and sometimes concrete trestles are commonly used to bridge particularly deep valleys, while timber trestles remain common in certain areas. The form survived, the material changed. The underlying logic, a repeating frame transferring load to ground, did not. The modern rail network stands on decisions made under pressure, with limited materials and almost no margin for error. If these forgotten systems are worth documenting, tell us which hidden craft or structure we should look at next.